Well, good morning. This is Thursday morning, the 29th of June, 2017, 8:09 in the morning. It's supposed to be a differential equation class, Math 238. However, I'm the only one in the room. The system has been very slow opening up this morning, so I'm a little late getting it done. There's guys out in the hall, the maintenance folks are out in the hall, all up and down the hall with ladders in the ceiling and doing things, so I don't know if there's something wrong with the system, that it's really slow and I have a bad connection here or something, but we are here. Did want to let you know one announcement, an apology basically. I have been, even though I'm teaching 6 classes this summer, 5 of the 6 are 4-hour classes. 3 of them have labs. This is the only class I have that's just a 3-hour class. And I'm in class on Mondays and Wednesdays from 8 in the morning till 9 in the evening with 2 20-minute breaks and 2 10-minute breaks. And that's it on Mondays and Wednesdays. No office hours to speak of. Hardly time to eat. Well, I've never gotten a whole lunch eaten in those 2 20-minute breaks and 1 10-minute break. Last night I was able to finish my lunch after 9 o'clock, so it was that was my last 10-minute break. So anyway, in spite of all that, I've only got 2 hours of office hours from 10 to 12 today. That includes lunch, and then from 3:30 until 5:15 this afternoon, and that's all the office hours I have on Tuesday and Thursday. That's all I have for all week. And yet I've been assigned to a screening committee for a biology position. Well, I'm not a biology instructor, but they've decided to put me on that committee. So they were supposed to meet Monday, but I couldn't meet Monday because I had classes all day. So I went over to do the screening on Tuesday and found out they've gone to a completely internet system, and it wasn't working, and they didn't have any paperwork, so it took them about 30 to 45 minutes. Well, first, a 30-minute wasted drive over there because I could have screened from my desk here. Then another 30 to 45 minutes while they were trying to get the login to work and that type of thing. Then I started screening, and the system went down once or twice while I was screening, but I was able to get 3 out of the 18 candidates screened before the person over there had to leave, so she had to kick me out. So, yeah, and I still got others to do. So as soon as office hours are over, as soon as this class is over, for the next hour, I'm going to be trying to screen as many candidates as I can. I can do that from my office now, so if the system will work. And then this afternoon, after 3:30, after my lab this afternoon, I'll screen as much as I can, but I've got to leave by 5:15 today. So in other words, why am I telling you this? Some of you have turned in, at least one of you have turned in some papers. I've got them, and I think I even maybe started grading them, but I haven't finished grading. I've got stacks of papers to grade because every spare minute I have and have had has been spent screening, and it will go on probably into the weekend. Hopefully sometime before the weekend's over, I'll be able to get the grading caught up and then get the grades out there on Blackboard and get your attendance in. But I can't say for sure that's going to happen. It's going to happen at some time. Whether I get it all done this weekend, I don't know. So anyway, that's my sob story. But in case you were looking for your scores, that's why you're not seeing them, because I'm having to be tied up with screening biology. And by the way, the 3 that I was able to screen, 2 out of the 3 had been screened by the chair incorrectly. So it's not like I could just thumb through them. I've got to read them all because 2 out of 3 were wrong of the first 3 I've looked at. So anyway, let's move on. We're in Chapter 2, which is first-order differential equations, 2.4 exact equations. We just started it last time, and we're at the top of page 65, differential of a function of 2 variables. So here's the deal. I've got to get my pen set up. Okay. We've got, let z equal some function of x and y. Okay. So this is a function of two variables with continuous first partial differential derivatives. Okay. We haven't been dealing with partials yet, but now since we have a function of two independent variables, you have to deal with partial derivatives. Now these are continuous partial derivatives in a region R, some region R of the xy plane. That's where the independent variables are in the xy plane. Then recall from calculus that its differential, if you remember this from calculus, dz is equal to, now this isn't derivative, but differential, dz is equal to the partial of f with respect to x times dx plus the partial of f with respect to y dy. Okay? That's the differential of a two-variable system. If it was a three-variable system, a seven-variable system, you just keep on adding terms. If there are that many independent variables, which you're not going to run into, that's what you do. Now, in the special case where f of x, y is not some variable z, but happens to be a constant 0, if that's the case, then the dz is 0, so this thing is equal to 0. Okay? Now, in other words, given a one-parameter family of functions, f of x, y is equal to c, we can generate a first-order differential equation by computing the differential on both sides of the equality. Okay? So let's see what that yields. That's sort of a nebulous kind of statement. Let's see what they mean by it. X squared minus 5xy plus y cubed equals c. Okay? There's an equation, f of xy, that's equal to some constant, and they're calling that constant parameter here. Okay? Now, if you take the partial derivative of that equation, that would be, with respect to x here, you'd have 2x partial of, I'm sorry. Okay. Hang on for a minute. Okay. 2x dx, okay, partial of the first term with respect to x, minus, and here's the partial of the first term with respect to y, that'd be minus 5y, with respect to x, dx, but then that has a partial with respect to y. The first term didn't, so you also have a minus 5x dy, and then the last term only has a partial with respect to y, and that would be plus 3y squared dy. Take a derivative of the right-hand side, you get a 0. Okay? Now let's group together. Well, good morning. Good to see you. What's that? Now, I'm beginning to think that maybe you and Marcus don't like each other. Because last week, he was here on Tuesday, you were here on Thursday, and the other wasn't. This week, he was here on Tuesday, you're here on Thursday, and so far, the other wasn't. So, are y'all doing tag team? You know, I guess so. Really boring talking to myself. It's going to take a couple couple of minutes for the projector to come on. Let me say again, because you did get here now, you may not go back and listen to the first part of this. I'm behind in grading, and it's liable to continue that way for a little bit. I've been assigned, even though I'm teaching 6 classes, 5 of the 6 are 4-hour courses. This is my only 3-hour course. This is my easy course this term. My light course, not easy but light. 3 of those classes have labs with them. That's why they're 4-hour classes. My Mondays and Wednesdays are booked solid from 8 o'clock in the morning till 9 o'clock in the evening, with one 20-minute break at 10:40 to 11, another 20-minute break from 1:40 to 2, and then somewhere in the 2 physics classes, 10 minutes to set up labs. There's not really breaks, but yeah, times when I'm technically not in class, but I'm setting up a lab or something. Okay, so I have no office hours Mondays and Wednesdays. And on Tuesdays and Thursdays, I only have the 10 to 12, and 1 hour of that is supposed to be my lunch, which I usually eat in my office. It's office hours too. And then from 3:30 to 5:15. Though most Tuesdays and Thursdays I stay past 5:15 just to try to catch up on stuff. Well, with that as a schedule, they decided to assign me on a screening committee to search for a biology instructor. Well, I'm not a biology instructor. Why? I don't know. Just to share the joy, I guess. So they wanted to have they had set aside 2 times for us to screen on Monday. I couldn't screen on Monday. I was in class all day long. And this is over on the other campus too, by the way. So I said the best time for me to screen would be after 4 o'clock on Tuesday, because I finish lab at 3:30 and it takes me about 30 minutes to get there. They said that'll be fine. So I got over there and they said we had to be there, okay? And before, I've been on screening committees before, they have piles of applicants and stuff like this, resumes and all this stuff, and they're very well organized and stuff, but all the stuff has to stay in that room. Well, I went over Tuesday and they said, oh, you do this online now. Well, I could have been doing it from my office, except for the fact the online system wouldn't let me log in. So they had to call people and do this and do that and do that. It took about another 30 to 45 minutes before I could even log in. Okay, so I logged in and started the process, learning as I went. And it wasn't that hard to learn, but it was just slow, because it's all you have to wait till the files load and stuff like this. The system crashed twice during the time I was there, but it came back up. And then at some time, 6 or 6:30 or something like that, the secretary had to leave and she had to chase me out because she had to lock up the room. But she let me carry all the files with me that they said you had to leave in the room. She said, well, no, you need to do these. So I've got them with me, and that means Tuesday afternoon I got no grading done at all because I was over there doing that. Couldn't do any yesterday. And today, as soon as I get out of this class, screen. And then I'll teach my afternoon class and screen. Don't think it's possible, but I'm going to try to get all those finished today. But today is one of those rare Thursdays when I do have to leave at 5:15. I don't have the option of staying later. I've got to be in Homewood, which is not that close from here, before 6 o'clock because the business closes there. I've got to be there before they close. And that's rush hour. So I've got to leave by 5:15 to guarantee I can be there before 6. So, long story short, I have gotten no grading done this week. Well, while the students were doing labs in physics, I sat down and graded as much as I could, which is maybe 1 or 2 papers or 2 or 3 or something like that. Here's a stack that's not graded, and I'm going to probably get more today. So, things are just not going to get done until I get that stack done. Now, the other bad news on top of that is they're going to want to interview candidates. And if they do it on a Monday, Wednesday, I don't know what I'm going to do because I'm in class all day. So my guess is maybe to accommodate me, they'll do it on Tuesday, Thursday, which means I don't know what we'll do about this class, but we'll try to figure that out later. Okay, so anyway, if you notice things aren't done, that's why they aren't done. All right, what we're doing is we're in Chapter 2, which is first order differential equations. 2.4 is exact equations, and on the, it's not really an example, but it's the thing at the very top of the page there. And I just, okay, the deal is here, what if you had a function with two independent variables? Okay, two independent variables. The differential of that, because you've got two independent variables, you deal with partial derivatives. This is the first time we're dealing with partials in here. So, the differential of this was dz, you can go back to Cal 3 probably and find this. dz is equal to partial of f with respect to x dx plus the partial of f with respect to y dy. Now, that's somewhere on a region in the xy plane because those are your independent variables. Okay? Now they said, what if this z was a constant? I put 0 there. It could be 0. But what if it was any constant? Okay? Well, derivative of a constant is 0. So this side, I moved it over here, would be 0. So this thing would be 0. So basically, that's the type of situation we're going to find ourselves when you have an equation, and they call it a one-parameter equation because the thing is not a function over here, but just a constant. That becomes a parameter. Seems strange use, but it is. And then, what do you do to determine the differential equation from that? Well, because you have two independent variables, you take partial derivatives of this, just like we did here. This has no y dependence, so the only partial here is with respect to x, be 2x dx, just like here. This one has both x and y dependence, so you take the partial first with respect to x, which would be minus 5y dx. Then the partial with respect to y, which would be minus 5x dy. Okay? And then you take the partial, since this has no x dependent, only with respect to y, so the part 3y squared dy. You take the derivative of this, you get 0. So this is, that's right where I left off. What we do now is group the differentials together. That gives us a 2x minus 5y dx, and I like to put it with a plus sign, plus 3y squared minus 5x dy equals 0. Okay? Now, they put the minus 5x in front. It doesn't matter. Now, it says here, of course, not every first-order differential equation written in differential form will come out this way. But this is then given the generic expression of m of xy, usually polynomials, doesn't have to be, usually a polynomial function, mxy dx plus n, I can't write, and I won't erase, okay, plus some n of xy dy equals 0. If you can get, if it comes out into a form like that, corresponding to some equation, f of xy, like we had there, is equal to c, some constant, parameter they call it. But if you do wind up with one of these, and thinking of it the other way, if this was your differential equation, how do you find your f of xy? That's what we're going toward, okay? If you're given a differential equation like that, is there some way to recognize that the differential expression is a differential of some function? If there is, then an implicit solution would be that one parameter system. That's why they're calling it a parameter, okay? Because what we're going to do is start with a form like this, and if we can work backwards to get to this, then that would be a one parameter system. Because this is equal to 0, the integration of that would be a constant. Okay, a parameter. So this then leads to your, do you say you do have a book? Yeah. Okay, all right, so I won't write this down. The definition 2.4.1, an exact equation. I have yet to figure out why they name it that. An exact equation. A differential expression such as this, m of xy dx plus n of xy dy equals 0, is an exact differential. Okay, I understand the differential part. That's in differential form. Yes, I got that. Why is it called exact? Okay, is an exact differential in some region R. So this will be in some region R of the xy plane, because that's what your independent variables are. If it corresponds to a differential, to the differential of some function f of xy. If when you process this, that produces some function of x, y, defined in R, then this is an exact differential equation. Okay? Said to be an exact differential equation if the expression on the left-hand side is an exact differential. So that's where it comes from, if it's an exact differential. Okay, so let's go to a clean slide here and look at a new example. Here's one. X squared y cubed dx plus x cubed y squared dy equals 0. Okay? Now, that's a very symmetric seeming equation. They don't have to be, this is, but they claim it is an exact equation because the left-hand side is an exact differential of this. D of 1/3 x cubed y cubed. Okay? Pretty symmetric looking itself, isn't it? And if you take the derivative, the differential of that, let's do it, with respect to x, because you got two independent variables, first with respect to x, so the partial of this function with respect to x will be 1/3, 3 times 1/3, which is 1, x squared, y cubed, because y you treat as a constant when you're doing partials, if it's with the other, and that's your dx, plus, and take the partial with respect to y, 3 times 1/3 again is 1, so that would be x cubed, y squared, dy. Sure enough, that's exactly this, and as long as that was a constant, then that would equal to 0. Okay? Notice that if we make the identifications, m of xy equal this, so this is your m of xy, and your n of xy to be that, okay? Now here is the test. This is how you tell if it's going to work or not, okay? Take the partial of this m with respect to the other variable, with respect to y, okay? And see what you get. This is your m of xy, so take the partial of that with respect to y. What do you get? Yeah, okay, x squared, okay, 3 x squared y squared, right? Yeah, right. I just rearranged. Yeah. Your x squared, because you take with respect to y, you don't mess with that. That's just treated as a constant. this will give you a 3y squared. So I put the constant out in front, so it would be 3x squared y squared. Okay? Now, let's also take the partial of n with respect to x, with respect to the other variable, and see what we get. And surprise, surprise, what do we get? 3x squared, y squared. Guess what? Those two are equal. If those two are equal, that means it is an exact differential. Then you can use the techniques that we're going to do. Notice that if we do that, you find out those are equal to each other. The next theorem shows that the equality of the partials is no coincidence. So, let m of xy, this is, if you got your book, it's in there, bottom of the page 65. If m of xy and n of xy are both continuous in this area, this region that you're talking about, m of xy and n of xy are continuous and have continuous first partial derivatives in a rectangular region R that's defined by x is between a and b, y is between c and d. Okay, now in that little phrase there can come the thing that will reach out and snag you and possibly make you make a mistake. Okay? If that range, let's say the a was -1 and the b was 3. So x is between -1 and 3. And the y was whatever. Okay? If you had a function that had x in the denominator, and if x ever became 0, that's not defined in that region, because 0 is in that range. So number one, you've got to have the function continuous in that region. But not only the function, the derivatives of the function, the partials of the function, have to be continuous in there as well. So even though the function may have been defined at x equals 0 or at some other value, if the derivative moved it down there, for instance, if you had x to the 1/2 power, that's fine at 0. The square root of 0 is 0. But when you take the derivative of that, you become x to the -1/2 power, and then a 0 doesn't work. So you have to watch out for those conditions. They have to meet those conditions. And they are, again, the m and the n, these two functions that are when you write this out in exact differential form, they have to be first continuous and have continuous first partial derivatives in the rectangular region defined by x between a and b and y between c and d. Then a necessary and sufficient condition that m of xy plus dx plus n of xy dy be an exact differential is that the partial of m with respect to y must equal the partial of n with respect to x. If that fits, you're in good shape. All right, now they go through a proof here with some assumptions and stuff. Do you feel like that would be beneficial for you to go over, or are you okay without it? Huh? Okay, thank you very much. It's not a bad proof, but read through it if you'd like. It certainly comes out quite nicely. So that, second? Okay, and that's the sufficiency part, okay? Okay, now I don't know if they're going to do the necessity part. It's necessary and sufficient. So that's the necessity part. The sufficiency part consists of showing that there exist a function. So I'll let you read that too. So let's get down to the brass tacks. How do you find solutions? So let's say that we do have an equation in differential form. Okay, let's clear this screen here. Say we have an equation that's m of xy dx plus n of xy dy equals 0. Okay? It has to look like that to begin with before any of this other stuff matters. Okay? Now what we have to decide is and let's say that given this, determine whether the equality holds. So the partial of m with respect to y is equal to the partial of n with respect to x. Okay? If it does, and let's assume that it does, then there has to be some function f of xy. If that equality holds, if partial of m with respect to y is equal to partial of n with respect to x. If that holds, then there must be a function, this is the necessity part, some function f of xy such that you can take the partial of this f with respect to x, that's what will create this, and that has to be the m of xy. Okay? Now, you can find at least a candidate for that f by integrating this. Okay, and what do you mean by that? Let's rewrite that in differentials as, and this is a little bit messier with partials, but I hope you'll forgive me and let me go on and do it. I'm going to do df, even though it should probably not be that, is equal to m of xy dx, right? And if I take the integral of that and the integral of that, this would give me, that's the integral of a differential, that would give me the function f, right? Fundamental theorem of calculus, part 1, I believe it is. Okay. Now, if that exists, okay, and it does, we basically are told we can find that f, or at least some semblance of that f, by integrating the m of xy dx. Now remember, there is no, y is in here, but we're not integrating with respect to y. We're only integrating with respect to x. So, y is treated as a constant, right? So if that integral can be done, you're going to have to do, normally, if you're doing an indefinite integral, then you put a plus c at the end, right? However, because you have this other variable y in there, that c may actually be a function of y, because it's treated as a constant, okay? So if that integral is doable, okay, then there could also be, this would be that integral, whatever that value would be, m of xy dx, and then your constant of integration is a constant function of integration, and they name it g of y, because the y wouldn't have been involved there. Okay? Now, not a very satisfying function, is it? Because it's got an integral sitting in there. And you got y, and you got an unknown function g of y out there. But that's okay, because guess what we're going to do next? Okay? What we're going to do next is take the derivative, the partial of this, with respect to y. And what should that be? The partial of this f that we've come up with respect to y, that's going to be our n. So partial of f with respect to y would be, now, this is sort of the pain in the neck. You can't do it because you don't know what it is. Partial with respect to y of this integral, m xy dx, okay, plus, now g, remember, is a function of y alone. No x's in there. So that would just be g prime of y. Okay? Now, whatever that becomes, this thing right here, that's got to be your n of xy. Okay? It's got to be the n of xy. So, now, remember where we started? We know n of xy. That's that part, that piece in that exact differential up there. That's your n of xy. So we know that. And basically, we're assuming we know how to do this. We know how to integrate that m of xy because it's a continuous function. And then we know how to take the derivative of that. So all we're really looking for is this g prime. Because we don't even know what g prime is, or g is, so we don't know what g prime is. So let's solve for that. So let's subtract this thing from both sides of the equation. Now I've got to get some more room here. I've been too florid with, oops. Oh, I'm sorry, that is what I wanted. Okay. I sure hope I'm not going to need this any longer. I probably will, but I'll regret doing this. But let me fill in what I can here. Okay, so what we got is g prime of y is equal to n of xy, which we know, that came with the problem, minus the thing we just calculated, the partial with respect to y of the integral of m of xy dx. Okay? So basically, we need to figure out what that is. Now, just a little warning here. You may be used to, by that fundamental theorem of calculus, when you see a derivative of an integral, say, oh, those go away, and you just have the function on the inside. Not necessarily. If this variable is not the same as that one, no, don't even try. So we aren't guaranteed. But so far, we're just using symbols here. Guess what? We would have already done the integration if we could have, and we would have taken the derivative if we could have. We just don't know what the function is. It was given, but we just, it's just symbolic. So don't get too wrapped up in it. It's a lot easier than it looks like here, because you would have already done those operations. Okay? So then the last step, okay, we integrate that last equation. And I'm going to have to erase some more. And I'm also probably going to write a little bit more just to remind ourselves. What is y prime? It's d, g, dy. Right? Not multiply. Write this in differential form. dg is equal to n of xy minus the partial with respect to y of the integral of m of xy dx, all that times your dy. Okay? And then integrate both sides of that, and that gives you your g within some constant. Okay? So let's get this out of the way. Hopefully you don't need that, but you can go back and find it if you do. Your g, which is a function of y and y alone, is equal to this thing. Okay? And I'm going to put all that in a big bracket there. Now, it looks incredibly messy, but those are all things that you could do and could have done already. And whatever that integral is, I'm just going to do this, then you'll have to, of course, do a plus c at the end, because it could have an arbitrary constant. Okay? So, it says some observations are in order. First, it is important to realize that the expression n of xy is equal to minus the partial with respect to y of the integral m of xy dx is independent of x. Okay? because you're taking the partial, this thing, no, this thing right here. Where is it? Yeah, that line up there, that G prime of Y, okay? Okay. This looks like it's still got an X's in it, okay? It looks like, well, that one wouldn't have any X's in it because you've integrated those out, okay? So even though that looks like it's got X's, this is independent of that because this is a function of Y alone. So the X's in there are kind of like, don't want to say dummies, but they're not part. So important to realize that that expression, the one we have right there, starts with the n of xy minus the partial, with respect to y, that is independent of x, okay? Now, here is the reason they say that, okay? It's a little, okay, let me, need to erase something. Let's see if I can pick out what I need to erase. I guess it's this thing down here. I'm afraid I might need it, but it's too bad. I just don't have room for it. Not the way I've been scrawling all over the page today. Okay, this thing right here, if we were to take the partial of this with respect to x, okay, that'd be n of xy minus the partial with respect to y of the integral of m of xy dx, okay? I'm just doing this part, not the integral part, just that part, okay? So that's what I'm doing. What we're trying to show is that this part right here, this part here, is a function of y and y alone. It indicates that over here because this is g prime, and that's a function of y alone, so this had better be. So here we've got to convince ourselves it is, because this looks like it's still got x's in it, okay? Well, let's take the partial with respect to x and see what we get. Well, this will give us, I think I'll write it here, the partial with respect to x of n of xy, right? Minus the partial with respect to x of the partial, let's see if they do it that way, I think so. They do one thing differently, but I'll get to that in just a second. Times the integral of m of xy dx. Okay. We're taking, that's the partial of that. Okay. Now here's a little trick. I don't know if you remember, hopefully you do, when you have mixed partials like this, if you've got good, continuous, well-behaved functions, you can reverse the order. Okay? So I'm going to do that now. Okay? I'm going to reverse the order of that and make this part the y and that part the x. Okay? Because that's true about partials. Okay? If you got a good, well-behaved function, that's true. Now, by doing that, however, look at this, because that is referring to the same thing, right? Your independent variable is x in both cases. Now we can apply the fundamental theorem calculus part 1. And this just gives you m of xy. Sure, because you're taking a derivative of an integral, both with respect to this. You couldn't do it here because those were not the same. You can do it here because you reverse the order, and this just merely gives you m of xy. Okay? So this thing right here is your m of xy. Okay? But notice what we've got there. We've got the partial with respect to x of n of xy minus the partial with respect to y of m of xy. And if you remember, the partial of m of xy with respect to y has to equal the partial of n of xy with respect to x. That's our condition that this was a thing. And that is met here. We assumed that from the beginning, so this thing turns out being 0 because those are exactly the same values. And if the derivative is 0, that's what we started with respect to x, that means there's no x dependence. That whole mess over there is basically a function of y and y alone. Now, obvious what happened to that x in there, but we've just shown that is a function. Well, we won't mess with it any, but that is indeed the case. Now, I don't know if that was worth it to you, but it is to give you a warm and fuzzy, I'm sure. Now, that's the first thing. Secondly, we could do just as well by starting the foregoing procedures with the assumption that partial of f with respect to y is n of xy. You integrate the n with respect to y, then differentiate the result, and you would find analogous equations, and it works out. Now, after doing all that, notice the last line on the page. In either case, none of these formulas should be memorized. Okay? Please don't. That's not how you work these. You work them by doing the, like I said, every step of the way there we could have integrated. We could have taken the partials. You didn't have to keep all those symbols in there. So please don't try to memorize those formulas. Remember the procedure. Don't try to memorize the result. So here we go. They're asking us to solve this. 2xy dx plus x squared minus 1 dy is equal to 0. Okay? Now that's a differential equation, actually in differential form. Do we know whether this is an exact differential or not? Say again? Not yet. How do we determine if it is? The partial of the m xy, which is this thing right here. So let's not even write m anymore. I mean, not forever, but let's just write what it is. Okay? The partial of 2xy, that's your m of xy, with respect to which? No, y. The other one. Okay? If this is that, then... Huh? Yeah, then this, now this is your test. Yeah. Okay? And you want to see, is that equal to the partial of the n of xy, which is x squared minus 1, with respect to x. If it is, we can proceed. If it's not, you don't have an exact partial differential. Okay? So, what is the partial of this with respect to y? No. With respect to y, that would be 2x. Treat the x as if it's a constant. Okay? And what's the partial of that one with respect to x? x. Yes, it is. So we know it is an exact partial, an exact differential equation. That confirms it. Okay. Now, Always do that first, okay? And confirm those. What's that? Well, okay, it depends on what the problem said. If the problem said, is this an exact differential equation? If that's not, yeah, you say no and go to the next one. If it says, solve this differential equation, and it's not exact, you don't say, well, it's not exact, go to the next one. No, then you have to use one of the other techniques. Linear, separation of variables, something else to solve it. But if it says, is it exact or not, and if you find out that's not true, you say no and go to the next one. So it depends on what the question is. You're trying to trap me, aren't you? Okay. So you said that if it wasn't, you can go to the next problem. Okay. Now, so what we're going to assume, since it isn't exact, we're going to assume that there is a function, f of x, y, okay, such that the partial of that function, partial of f with respect to x, is this m of xy, 2xy, right? Okay. If this is partial, that has to be true, okay? And that the partial of f with respect to y is going to be your x squared minus 1, okay? That's your n, okay? All right. So what we do with the first of those, like we said before, is write this as partial. I like to do it as d because this is easier to write. df is equal to the integral of 2xy dx, right? And we can do that. That gives us f is equal to, what is the, now this is an integration with respect to two variables, so you're doing with respect to x, so you treat the y as constant. What would that give you? X squared y. Perfect. But not quite. You would normally do plus a constant, but because this, you did it with respect to x, this constant may be a g of y, right? Just like we did before, okay? Now that we've got some representation of that f now, let's take the partial of this f with respect to y. And what is that? Second? Okay. You're taking a derivative, partial derivative of this with respect to y. Yeah. Up there we did an integral. Now we're doing the derivative. Okay. It's designed to be confusing. Okay, right? Okay, what? So x squared. That's all it is. You treat the x's as a constant. Constant times y, derivative of that would just be the constant. X squared. Plus g prime of y, right? Because you got to take that with respect to y too. But what is this partial of f with respect to y got to be? From what we had before? X squared minus 1. Well, there's the x squared. So this implies that g prime of y, in fact, I'm going to rewrite that Leibniz notation because it's a little handier here. More awkward, but handier. dg dy is equal to a minus 1, right? You see it? And if dg dy was equal to minus 1, that means dg is equal to minus dy, right? Integrate that, and you get g is equal to minus y plus c. Right? Okay? Now let's back off and see what we've got. This is g of y. Okay? So f of xy, which should be the solution to this exact differential equation, is equal to, this comes from here, x squared y minus y plus c. Okay? So, there's your solution. One parameter system. Okay? X squared y minus y plus. Okay. Now, what you could do is say that's a minus c, okay? Or that's equivalent to saying that's equal to c. Now, that almost feels like a little bit of a sleight of hand here, but it is okay, okay? The explicit form of that solution, so if you, now not all of these will have explicit forms. What they mean by that, you can solve x in terms of y. I mean, solve for y in terms of x. You could factor out a y from both sides here and give you x squared minus 1, right? That's equal to c. So then divide both sides by x squared minus 1, and you get y is equal to c over x squared minus 1. So that would be your explicit form of that solution. Not all of them you can do that, okay? But, big but here, okay, sorry. From this solution, you can see x cannot equal plus or minus 1. So that means if you're doing some region, remember that was the assumption, you've got some region here, the region can't include either x equal 1 or x equal minus 1. So your x's could go from minus 17 to minus 3. No sweat there. Y's could go, I think, just about anywhere. Except, yeah, I guess they could. Okay. Your x's could be minus 1/2 to plus 1/2. That would be okay. But they couldn't be, and even minus 0.9 to plus 0.9, or minus 0.99999 to plus 0.99999. But it couldn't include either plus or minus 1. But then also your region could be anywhere past 1, 2 to 3 million. You know, that's fine. Anywhere there, that equation will work. It will not work for, in other words, your region of integration cannot include x equal plus 1 or x equal minus 1 anywhere in it. Okay? So. All right. It says, note that the solution of the differential equation in that example is not f of xy is equal to x squared y plus minus y. That's why I didn't like writing it in this form. Okay? Rather, it is f of xy, which is this thing, is equal to c. If a constant is used in the integration of g prime of y, then we can write the solution. Wait. If a constant is used in the integration of g prime of y, in other words, where was it? This step right here. If that just came up to be, then it may be that f of xy is equal to 0. That's not a very clear statement there. What do they mean if a constant is used in the integration? We might see an example of that later. Let's move on. Example 2. Any questions about this one? Okay. That first one's so easy. Let's get it a little more complicated, don't you think? Oh, why not? e to the 2y, all right, that's sounding that way, minus y cosine xy. Oh, this isn't complicated at all, is it? Whoa. Dx plus 2x e to the 2y minus x cosine xy plus 2y dy is equal to 0. All right. Okay. Wait a minute. This isn't differential form. Some function of x and y here, that by the way, okay, y is your m of xy, dx plus, oh, I forgot to open my parentheses here, okay, plus some other really complicated looking function of x and y, dy is equal to 0. Up till now, we've been using sort of polynomial-looking things. Now we've got variables, we've got exponentials, we've got trig functions. Yeah, we got it all almost, don't we? No logs in here yet. But is there any chance that could be an exact differential? It could be. It doesn't look hopeful, but it could be. How do we check and see? Partial of this thing, e to the 2y minus y cosine xy. Make sure I got all the terms in there. Yeah. Take that partial with respect to what? With respect to y. Oh, I was hoping you were going to say x, because then you throw the first term away. Nope, you didn't, did you? Okay, so let's go for it. What's the partial of e to the 2y with respect to y? E to the 2y times 2. Okay? That wasn't too bad. Minus, here we have a product rule, right? Inside part of the product rule, you're going to have a chain rule. So we'll worry about that tomorrow. Okay? I'm just kidding. That was a line from Gone with the Wind. Worry about that tomorrow, because tomorrow is another day. Okay, so how do you want to do that product? Y times, and it's actually a minus, times a minus sign, so that makes it a plus there, of xy. But then you've got to do the chain rule with respect to y, which would give you an x. Yeah. Okay? Okay. That's it. No. You got the other half of the product rule. Remember there was a minus there. And what does that produce? Which is 1 cosine xy, because that's the other function. So there's the partial on this side. Let's do this one. The partial of this thing, 2x e to the 2y minus x cosine xy plus 2y with respect to what? X. Okay. Now, this isn't quite so terrible. Why? Especially that first term. Okay, I can't hear well. Yeah, you're doing the partial of this thing right here with respect to x alone. there's the only x. So all this other, the 2, the e to the 2y, they're all treated as constant. Times x, you would just have the constant, which is 2e to the 2y, right? So this gives you 2e to the 2y. That's looking pretty good, isn't it? Oops, but we still have another product rule. So how do you do this one? Okay, I'll put the minus there. X times. Okay, so no, derivative of cosine is negative, so that makes that positive, right? Sine of xy. But then you got chain rule, and then you got a y there. Okay, good. Then you got, remember the minus was there, minus cosine of xy, right? Derivative of x is 1, okay? But then the partial of 2y with respect to x is, it's just treated as a constant. The partial of a constant, the derivative of a constant is 0. Hey, look at that. We can't do this. Yeah, it's with respect to x. If that had been with respect to y, it would have been a 2. But it's with respect to x, it's a 0. Okay? They work. That means, guess what, team? This is an exact partial exact differential equation. Okay. I was almost hoping it wasn't. Okay. No, it is. Okay, so where do we begin? Well, let's write down what we know to be true. This thing right here, remember, the fact these are equal, that guarantees you do have a function, f of xy, that is the solution for that, right? Now, since you have that solution, you know that the partial of f with respect to x is going to be this m, right? That thing right there. That's going to equal e to the 2y minus y cosine xy. Okay? But writing that in differential form and then integrating, okay, this produces just f of xy, right? Oh, no. Okay. Now let's integrate that one with respect to x. Yeah. E to the 2y. Okay. X e to the 2y. I mean, normally I'd put it on the other side. But this is a constant, remember? It's a constant. A constant, integrating a constant would be that constant times x. Okay? Except I don't like to write x here because then you might confuse, well, is that x with the y or is it, you know, so if I put it out front, it removes all that. Okay. So there's that first part. Now let's do the next part. And again, the y is treated as a constant. Let's pull that out. And the antiderivative of cosine xy No. The y, remember, if you're integrating with respect to x, the y is a constant. Pull it out. Okay? Now, we just have an integral of cosine xy. Think of that as cosine 7y, or something like that. Remember, the y is just a constant. What's the antiderivative of cosine? Okay? And that is sine, because so we keep the sign, the SIG and sign the same. So that would be a sine of xy But remember that y is a constant. If that had been a 7x, then you have to unchain rule it and divide by the y. But guess what? Not a bad thing to do, is it? Okay, so you got that plus what though? Second? You would be a c, a constant, but remember you're treating your y's as a constant, so it actually could be some g of y. It's sort of equivalent to a constant, but not quite a constant, okay? A constant with respect to x, but it could have y dependence in it. Okay? Now that we have a representation of the f, then what do we do next? Yeah, take the partial of it with respect to y, the other one, okay? So I've got to find some room to do this. The partial of this f with respect to y would then be, now do that part. Start with this term, the first term. That's the partial of this first term with respect to y. This term right here. Yeah. Partial of this f, and we're going to do it a term at a time. X, that's your constant. Treat it as a constant. E to the 2y times 2. You got it, okay? Let's go to that next term. Remember, those y's are out of there now. The partial of sine xy with respect to y. Okay, yep, you're going to have an x. Cosine xy. And then you got your plus g prime of y, because the derivative of that with respect to y. Okay. Now, you're taking derivative of this one, right? Okay. Derivative of sine is cosine. So if the minus sign was there, it stays there. Sine of xy. But the derivative of xy with respect to y would be your x. And that's where the x came from. Right? Plus that. Now, remind ourselves, what is this df dy? That's your n. That's the n. So here you have your 2x e to the 2y. Fantastic. Minus x cosine xy. Fantastic. This tells us g prime of y is what's left? 2y. That's it. The g prime of y is 2y. G, which I'm going to write is dg dy is equal to 2y, which now I integrate. Integral of dg would be g, and g is equal to integral of that. Y squared plus c. Okay? Now, that plus c sort of gets in the way a little bit, so let's see what we've got now. Our f, right here, we now know what g of y is, okay? So now we can rephrase our f, and if it's okay, I'm going to erase a line up here. Let's erase this one. I hope I won't regret it. Yeah, because that was just verifying. In fact, I could have done the one on top. Let's erase all that. Okay. That was just making sure we could proceed. We could, we did, we conquered. No, or something like that. Okay. That was just our verification step, that we could do what we wanted to do. So what is our f? F of x what? Yuck. F of xy is equal to x e to the 2y minus sine of xy plus the g, which is y squared. That's your f of xy, okay? And you set that equal to the c, okay? Because the derivative of that is equal to 0, okay? Now, now, do you think you can solve this explicitly for y? No way in the world, okay? You got a y stuck in there, a y stuck in there. That one would be bad enough because you'd have to take square roots, but no. This one cannot be solved explicitly for y. So there's sort of a lot less telling here. It looks like to me x is completely unrestricted. I don't see any restrictions in x. And frankly, I don't see any restrictions in y either. So I think this would be good for y between minus infinity and positive infinity, x between minus infinity and positive infinity. Let's see if they picked out anything that would be a little bit different. So they wound up with x e to the 2y minus sine xy plus y squared. And now they put the plus c is equal to 0. That's what I did last time. They put it the other way, so I did it their way this time, and they left it there. I guess that's because they were going to solve for y. So this time we'll leave the plus c is equal to 0. Okay. Now, in that case, leave that out. Okay. Don't put the because the f of xy is just the xy part, not counting the c. Okay. So if you put the plus c in there, don't count f of x. Don't say it's part of f of xy. Okay. And by the way, they used h rather than g. I don't know why. Okay. Now, I know we don't have much longer to go, but I need a pot of break, sorry. So let me just, okay. That was example 2. Ready for 3? Was I not recording? Had I turned it back? I thought I had, but I'm recording again. I hit the wrong thing down here. My sin x became 6. I get to talking faster than I write. Sin x dx. Okay? Now, I'm going to, is it okay to do two things at once? I'm multiplying that denominator there by my dy, but I also want to bring it on the same side, so I'm going to flip and write this plus, that would have been all right, plus y times x squared minus 1 dy is equal to 0. That's our standard form. Now, just multiplying by the things right in differential, you get them on two different sides, so I don't have to pull one over. So I pulled it over, subtracted it, but then rather than having the minus sign here, I just reversed the signs here. Now I could have left that alone and reversed these two, and that would be good. I hope that wouldn't have been easier, but let's see. That's in exact form, but we still don't know if it's an exact equation, do we? How do we tell? Do our test. So let's do the partial of this thing, x y squared minus cosine x sine x. I almost did it again. With respect to what? Y. Okay, and see what that gives us. I'm sorry? Oh, I can't hear. I'm sorry. X is treated as constant, exactly. Okay. 2xy. Because x is a constant, okay? Okay. Minus. Huh? No, the thing is, those are all functions of x. Both of them are. There is none. So that's it. That's all, folks. Okay? Now, let's do this one. What do we do here? Partial of this thing, y. Let me, you know what? Let me go on and just write this, multiply that through. It'll be easier to take a partial of. X squared y minus y. What's that? Not really, but sort of. But I think it's a little easier this way. And what do we take that with respect to? X. And what does that give you? 2xy. Guess what? They are indeed the same, so we can proceed. How do we proceed? Okay. Okay. Let me erase some stuff because I know I'm not going to have room the way I've been writing all over the board here. All this was a verification that you could. We know we can, so we don't need that anymore. Okay? So, let's write down, oh, I erased the equation too, sorry. Okay, x y squared minus cosine x sine x dx plus, I like to do it this way, and you know, I don't see any reason not to do it the way we just did. X squared y minus y dy equals 0. Okay, I erased too much before. That is basically what we had, except we had the x squared minus 1 times y. So I think that's going to be easier to work with. Okay, now, what were you going to say? Second? Okay, yeah. Yeah, okay. Now, the first thing we do is say, because that is an exact differential, because we just checked it and it was, that means there is an f of xy that is a solution. Okay? Now, what do we know about that f of xy? We know two facts. We know that the partial of this f with respect to x is what? That's it. xy squared minus cosine x sine x. Okay? Why? Because that is your m of xy. That's the partial of f with respect to x. And the other fact we know is that the partial of f with respect to y is x squared y minus y. Okay? We know that because there has to be some function. It's a solution because we verified it is an exact differential. So, and we know those two facts about it. Now, you want to take that first one or the second one, or does it matter to you? You choose. person, okay? Let's write that in sort of a differential form. df is equal to x squared y minus cosine x sine x dx, right? Integrate that, integrate that. This gives you f of xy, okay? That's the integral of the other one. With respect to x, okay, the y is there, I agree. Second? Okay, where'd you get that? Okay, you're integrating. Let's just imagine that was 7x squared. Now, the y is just a constant when you're integrating. That's the so when you say y, yeah, that's a constant. Pull it out. Integrating x squared. What would that be? Okay, x cubed over 3, right. So that would be y. So I'm going to put it x cubed y over 3. Is that okay? All right. Now, integrating, sorry, a minus cosine x sine x. What you reckon that would be? Second. That isn't a bad idea, okay? I think a better idea, though, would be substitution. Okay, so let's try that. Let's let, I'm cheating a little bit here, let u equal cosine x. Then, how does that go? What's the next step? Second? No, it's not. This is substitution. Okay. What did you just say? My hearing's bad, huh? Okay, the next part is say then du is equal to, only it's negative sine x dx. And guess what you have here then? We have the integral, I'm just going to do this part, the integral of u du, which is u squared over 2. Okay, but your u is cosine x, so can I go up and erase this? Because I know I'm going to need the room. So that will be plus cosine plus cosine squared x over 2. Okay? One more thing. Indefinite integral. G of y. Excellent. Or it doesn't have to be G. They use H sometimes. Or they use whatever. All right. Now. SpaghettiOs. Oh, yeah. Now, that's our f of xy. We know. We just don't know what the g is, but whatever it is, that's it. Next thing we're going to do is take the partial of that f, this time with respect to y, right? Because we already dealt with the x. What does that come? Take the partial. What do you get? Okay, say that one more time. Yeah, I'm not really happy with this right now. Okay, let's go on with it. That would be, there's something screwed up here, and it's probably me. But when you take that with respect to y, you get x cubed over 3. Okay? Yeah. Plus, what do you get there? Say again? Yeah, if x is a constant, that's going to be 0. Okay? And you'll get a g prime of y. This is not looking good at all, because you're supposed to look up there and see these are the things we should have here, and we don't. Let me see, where did I make my fatal flaw here? Okay, we got the first part, we already did that. You know what they did, and I was starting to suggest we do it, but then I wimped out and didn't. And now I'm really regretting it. Okay? Since this was much simpler than that, I said I was going to say, let's start with that one and then work backwards. Right. So it should work out either way, but it sure doesn't look very pretty this way. So let's go back. Oh, I'm sorry, we're out of time, aren't we? Aren't we? Yeah. Sorry about that. I wish I'd have gone with my first impulse, but I thought, no, let's try it. Yeah. Do you think you can finish that at home, or do you want to pick up on this next time? Okay. So first thing, unless you and Marcus aren't speaking again and you're not here, what I'm going to do is put a little note here. I'm going to put a question mark if that's where we're beginning. If not, we will begin below it. But I'll ask you, did that work out okay? And we'll go from there. So, sorry about that. We ran out of time. Well, let me give you some homework exercises. Oh, we almost finished the section. I think you could do any of the odds 1 through 19. And if you are successful in doing that initial value problem, then try some of the odds 21 to 25. And we'll hold off on the rest of those until later. Okay? Good deal. And with that, have a good weekend. Of course, working on differential equations will make it a good weekend, won't it? Yes. Right, of course. Okay. Good deal. Oh, and you have heard sort of the good news, bad news situation, haven't you? What? No, this is a different one, I think. Yeah. The good news is Tuesday is the 4th of July. Okay, the bad news is we won't have class. That is really bad news, isn't it? So I'll see you next Thursday. See you in a week. Have a good, great 4th of July.